Lectures. First, you have to go through lectures.
Through the lectures, right? Okay. Okay. Just a second. Let me share my screen. Uh, Sorry for the delay because there was a power cut in my campus, so that's why the session has been late by 15 minutes. Okay. So this week's lectures are based on the control of microgrid systems and its stability. So stability will be mainly covered in the next week. This week mainly covers the control and design of the DC microgrid architectures. So let's start. So as we have discussed in the earlier lectures, so if there is a AC network that is connected to the DC microgrid system using a DC to AC converter or an inverter, right?
Screen, sir. I need a full screen.
Yeah.
It will coming off. Minimize the scheme, sir. Full screen.
Okay. Just yeah. Is it visible now?
Okay, sir.
Okay. So in case of DC distribution system, when there is a DC distribution system and when your loads are of AC type, what do we connect? What converter do we connect? An inverter, right? Yeah.
Sure.
Okay. So in case of AC system, when they're connected to DC, it is connected to inverters. So in AC system, what we have are two fundamental quantities, actually three quantities, but the third quantity can be controlled based on these other two quantities, which is the voltage and the frequency, right? So this frequency is absent in case of DC networks. Now in case of AC generator, what happens is the frequency is mainly controlled by increasing or reducing the mechanical input power, and the voltage is controlled by injecting or absorbing the reactive power. So in power systems, we have learned in UG that P is dependent on
Frequency. Frequency
frequency,
depends.
and Q
Voltage.
is mostly dependent on voltage, right? So this we have learned in power system, and that's only is being repeated in the lecture. Now, so in DC system, what happens? As I told, voltage is only the unique quantity that has to be controlled. So there is nothing known as reactive power in DC voltage. So the active power only controls the voltage. So this is the basic difference between a AC and a DC system. Now what happens is these DC systems are connected through inverters. So the main thing that we have now are inverters. These inverters can be connected in multiple ways. But to control the power flow from DC side to AC side, because inverter converts from DC to AC, so to control the power from DC side to the AC side, two main control architectures are preferred. First one is master slave control architecture. Second is group control architecture. Okay, so two types of control architectures are possible. So two different methods are possible to connect the parallel inverters in a microgrid. First one is the master slave and the second is the voltage group. So first we have the master slave architecture. So to discuss master slave architecture, so both of these architectures are based on parallel connections of inverters to the load, and the control of the inverter is determines what kind of control architecture it will follow. So let's discuss the first one, which is the master slave control architecture. So this is the DC bus. Let's suppose this is plus, this is minus. From here, this is the inverter. And this is the load, right? Now the other inverters, I am drawing three inverters to explain the each form of architecture. This is another inverter, and oh sorry, this is the other inverter. So all the three inverters are connected in parallel, right? Now, so this is my VDC. Okay. Now let's suppose this is my voltage plus minus V1. So I want to control the power flow in such a way that the voltage at which we supply to the load should be fixed at V1. So voltage controlled at V1. So this converter is operated and controlled in such a way that the voltage to at the output of the at the input to the load is always V1. Now the other two inverters, let's name them INV1, this is INV2, and this is INV3. So INV1 is responsible for controlling V1, let's say this is V out 1, this is V out 2, and this is V out 3. So INV1 is responsible for controlling VO1 to V1. Once it is controlled to V1, VO2 and VO3 will also be V1, right? So we need not control the voltage in case of INV2 and INV3. Now let's suppose the power requirement here is P, and the power flow here that is happening controlling it to V1 is P1. So now what should be done is P minus P1 amount of power must be supplied from these two inverters. So this is obtained by controlling the current of, so what we now have to do is control the current of INV2 and 3, so that I2 plus I3 is equal to, I am representing it in terms of so this thing should be equals to P minus P1 divided by V1. So this must be controlled in such a way that the remaining power must be obtained by from inverter 2 and 3 through current control, whereas inverter 1 is responsible for holding the voltage and hence it undergoes voltage control. So INV1 is having voltage control, and hence it is known as the master converter. INV2 and 3 have control of current, and hence these are slaves converter. So what is the issue of master slave control architecture is that it is dependent on inverter 1 in controlling the voltage. Once inverter 1 for some reason it uh, gets offline, or it is removed from the load, the inverter 2 and 3, one of the inverter 2 and 3 needs to operate in such a way that this voltage has to be controlled. So there is a dependency on one inverter to control the voltage. The other inverters will operate in current control mode to provide the required power to the load. So any doubt? Anyone?
Sir, how the slave controller is controlling the current and master is voltage only?
So the control is done in such a way, like suppose in case of an inverter, how do you so you have the inverter, right? I am showing it for a single phase inverter. It can also be done for a 3-phase inverter also. This is a single phase inverter. And here we have DC. Now how do they operate? Like this is so in case of here let's name this to be Q1, Q2, Q3, Q4. Then we have the tank circuit, and then we have, let's say, the load. This is a filter circuit, and then we have the load. Now Q1 and Q2 cannot turn on or turn off at the same time. Same goes for Q3 and Q4 for obvious reasons, because if both of them turn on, it will basically short the DC bus. So the switching strategy that is done in such a way that Q1, Q2, Q1 and Q4 will turn on. So they are given one gate pulse, say G1, and Q2 and Q3 turn on. They are given G2, which is G1 bar. Alright. Now now what you need to do is so you have G1 and G2. Okay, so now what you need is a carrier wave. There is a carrier wave of very high frequency. Let's say this is of 10 kilohertz, which is compared to a sine wave, which is a 50 hertz. From this comparison, you will get some PWM signals of different widths. The magnitude of this sine wave, the sine wave is actually some m sine of omega t, where omega is 50 hertz, 2 pi into 50 hertz. So this sine wave is m sine omega t, is my this sine function, where m is the modulation index and this is our control variable. So this comparison gives me these pulses, and these pulses are, let's suppose this is G1. So G1 is given in Q1 and Q4, and G1 dash, which is G2, just a complementary pulses are given to G2 and G3, and hence we will get a square pulse of varying thickness like this. It will be thicker, then again thinner, so like this, and then after passing through the filter we will obtain the sine waveform, because the higher frequencies will be removed. So what I need you to focus on is that this sine wave is this is considered to be the reference, and this reference has a variable known as m, which is our control variable. Now if we control this capacitor voltage of the filter, so let's take this capacitor voltage RMS, and after sensing this voltage, let's compare it, sorry, minus, and this will be plus, with a VC reference, and then after passing through controller, we will get a M. This is basically, in short, the voltage control of an inverter, what you are asking. And instead of controlling this voltage, if we measure this current through the inductor and again compare it with our reference current, which is obtained in some way from the how much power is needed, from there we can compute how much reference needs to be set, and after controller it produces the required modulation index m, which is the control variable that we refer to as current control. So the inverter 1 here, it controls the voltage, and once the voltage is controlled at these two nodes, now what we need to control is the amount of current that needs to be sent to the load, and that is done using the rest2 inverters. Does that
Yes,
answer
sir.
clear?
Yes, sir. Clear, sir.
Okay, so this is the master slave control. So as you can see,
Sir, generally
mhm.
in DC means you have to do only voltage control. No need to go for current control, sir. But here you discussing current control also. Is there any need
In
in DC system?
mhm.
In DC, you have to concentrate only on voltage.
Yeah, because in DC what you have, V into I equals to power. Power is how much power it will consume, it's dependent on the load itself, right?
That will be a load requirement.
Load requirement. So once you set the voltage, current will be based on load requirement.
Okay, you have to control current also in the DC system.
Hmm.
Sir, if the master controller is not working, the inverter 2 and inverter 3 will togetherly work as a to supply the load. You said.
Yeah, then it will operate as a current controller, right? So these two are operating in current control mode.
Then
So yeah, what?
if how it became as a current control, then voltage how it will be controlled and fixed to the
Oh, okay,
same
I
voltage
got your
level.
question. So yeah, so voltage then won't be controlled. So it will control the amount of current required. Now the voltage will be fixed based on the power requirement. So in case of AC system, it's VI cos phi, right?
Then it may affect the loads, right?
Yeah, it may affect. It may affect. It will. The voltage will be determined based on the power requirement. So you know I, you know cos theta, based on the load, because load will decide the power factor, right? So then the voltage is determined
Yes.
based on those. It can be anything. Yeah, you are right. It can be anything, and it can also affect the load. Yeah.
Hello.
Go ahead.
Then master slave control is a control method is not a good one, right?
Yeah, means it's not that much followed. What is more followed is the group control.
Control. Okay. The main reason is behind this is the reason, right?
We have the.
Or any other reasons?
Go ahead.
Is there any other reasons? Hello.
Yeah, go ahead. Go ahead. Go ahead. I can hear you.
Is there any other reasons not using for the master slave control? Is there any other
Dependency
reasons?
on one converter on voltage control. So if that
Okay.
converter somehow goes offline, so there can be like you don't know, you are just controlling the current. So voltage can be anything. Uh, then the power flow, will it be stable or not? That still remains a question with respect to if you observe the dynamics of the whole system. So there are several issues that will crop up. So what here you are doing is one converter is saying, look, I am holding the voltage. The other two converters are accordingly pushing the current. So it is well stable system. Now, if the voltage converter fails, voltage controlled converter, then it becomes the whole system will not work as desired. That's what I'm saying.
Okay, sir.
Right. Uh, yeah. So any more questions? Any doubt? You can ask me. The next one is group control. Group control is okay. Let me ask you something. Um, the first converter has been controlled, the controlling the voltage, good enough. The second controller is controlling the current, also nice. Why do we need the third converter to control current? Like one is controlling the voltage, the second one is controlling the current. The other converter's voltage is controlled by the first converter. The current that will be supplied by the last converter will be dependent on the load requirement of the load. So why do we go for a current control in the last converter? Can anybody say?
Because of power requirement changes.
Yeah, load will take care of that. No, load requires this much of power, it will take. So why this converter is also controlled?
Don't know, sir.
The answer to this is basically the So active power flow is proportional to the, it's related to. In case of DC system, we don't need, if we control the voltage or one, as I said, the other converter will provide the current based on the load requirement. But in case of AC system, there is another term which is frequency. The frequency, it can disturb the frequency of the systems. So that's why we need to go for a current control in the last, in the remaining converters as well. Any doubt?
Go ahead, sir.
Hmm?
Go ahead.
Okay.
Okay, sir. Next.
So basically, what I'm saying is, if there is a power variation, P variation, so it may have so happen that the current remains same, but there is a change in the frequency throughout the system. Now, to tackle that, there is group control. Now, group control, how it tackles the situation is basically, now the inverters will mimic as a synchronous generator. What happens in synchronous generator is this thing. This is F, this is P. So as frequency is closer to the nominal frequency, which is this point, F naught, let's say F naught. As the power requirement increases, the frequency slowly reduces. So for some power, let's say P1, we will have a FO1. So thus we need not worry that whether 1 volt, one converter is operating at voltage mode, the others are in current mode or not. We need to worry. We will say that all the converters will operate in group control mode. So this is known as the PF group. The other one, there are two uh, groups. This is a QV group. It's also similar. This point being the V norm. For a given V1, we have a Q1. Now Q1 can be positive or negative with respect to how do we want to inject reactive power or consume reactive power. This is the QV group. Now how these now since all the converters are operating this form, so how it is done is, suppose you want to operate the, for one inverter I am taking the example, now all the inverters can have it. For one F star, sorry, not suppose you want your converter to provide P star and Q star, where P star is your active power that it will share and Q star is the reactive power that it will share. So these you determine using some algorithm, that is a load flow algorithm or whatever. So once you obtain these P star and Q star, what we will do?
P star Q star means reference, sir. References.
Reference is how much active power it should provide to the load and how much reactive power it should provide to the load. So I'm showing how group control actually is implemented in case of this kind of systems. So these are the reference points. Okay. So now what we do is we compare it with the actual power that it is sharing right now. So, now okay, I will have a K P. Now what is KP? KP is this slope here, and let's name this slope to be KQ. This will provide my del F. Similarly, clear? Any doubt in this implementation? Hello.
Sir, in group control, what we are actually doing means when there is change of frequency
Yeah.
from F0 to F1 due to certain increase of load, then
No, in
we
group
have to
control, what
give
I am saying
that
is
much extra power to maintain that.
no. Group control basically what it does is it will let the what it does is it will provide, suppose a given amount of active power and a reactive power. So once it provides a given amount of active power and reactive power, it will accordingly change the frequency and the voltage at the output.
That is also within the limits, sir.
Yeah,
That
it should be
frequency.
within the limits. So that is determined with the consideration of Kp and Kq, that limit condition.
Sir, if it violates with limitation frequency and the voltage, then what will happen? Then how it will they control the
And
actual
handle.
circuit?
No, control will still be done. See, what here it is happening is your frequency and voltage will be changed. So it will operate at some other voltage and some other frequency. Now you assume that there is no inverter. It is as if there is a synchronous generator. So what happens? So the voltage has dropped to some value, or the frequency has reduced to out of that, but that should be the control should be done in such a way that this does not crosses the limit. So how to assure that? That is assured, that can be assured using the choice of Kp and Kq, and how much is your range of P star and Q star. This will ensure that your del F and del V, the not del F del V, the actual F, this is the difference of frequency, but the actual F should be within the limits, or the del F should be within 5%, I guess, 5% of the F nominal, and del V should be of like the 10% of the V nominal. So that is ensured with your range of P star and Q star and choice of Kp and Kq.
Sir, sound is not coming.
Sound is not coming. Hello, hello, hello. Just a second. Let me check.
Yes, sir, audible, sir.
Audible, right? Okay. So yeah. So the variation that is determined with, so the P star cannot be anything. It has to be within a given range that it can supply from P star, like P star should be within an interval P1 comma P2. and Q star should be within an interval, and then choice of KPQI. This will set it within the limits. Now, once this is done, the
If
the
you go
power
for the beyond the sir, if you go for beyond the limitations, then how it will be controlled, sir?
that I too don't know. Like what I know is this has to be maintained. If this is maintained, KPKQ choosing and the limiting of the power, so it will always be within limit. Now, if we go beyond the limits, that basically there are several problems. First of all, voltage cannot be very low because there is a problem in if anybody is there from power system, you will know for sure there is a problem of voltage stability. Like for a given amount of power flow, the voltage can be I think in for a given voltage the power flow can be provided till certain point, and then the voltage collapses. So that the voltage stability issues are there. Also there is frequency stability issue, so those stability issues come up. So that's why the limits are being provided, so that there is no stability issue and proper functioning of the entire microgrid system. But if we go beyond it, exactly what kind of problems will come, I can't say. It is dependent on the system. But these problems can show up. Yeah. Any more question? I'm audible, right?
Sir, voice is not coming, sir.
Now it's audible. Hello. Okay.
Yes, sir, audible.
So yeah. So if we go beyond the limits, that will invite several problems. Like one can there be there can be issues of voltage stability, instability. There can be issues of frequency instability. So those kind of problems can be there, or the transient instability. Like so, in power system, people will know it better. So it's basically in there is a power flow equation which states that h df by dt, where h is the inertia of the system, is equals to p input minus p output. So this basically governs the uh, dynamics between the active power flow and the frequency. And so so that there is no such instability that come up, so that's why the limits are set to those values. And also there is a proper power flow having a good voltage profile and a good frequency maintained at every buses. So for that reason, those limits are being mentioned. Yeah. So any more question or I'm audible, right?
Yes,
Hello.
sir.
So okay. So let's move forward. So this is a master slave. This is the control, and then we have the droop control. After droop control, what we have? Okay, now control of the voltage source converter, voltage source inverters basically. Now how each individual inverter is controlled. So this is the control architecture that we spoke of. Now after this, after obtaining del f, so now del f has to be such that it is reduced to 0. So it is basically now it will be compared to 0 basically. So such that del f is made 0 and del q is also made 0. Now as I was discussing, how each inverter is controlled. So it's by controlling the modulation index m, which is the control variable. So to obtain the control or small signal expressions, how do we achieve the small signal expression is provided in this portion. So what we can write is we can write a KVL expression at the output of the inverter. So how this expression can be written? So here this is an inverter, right? So let's say this is plus minus V1 and this is plus minus Vc.
Sir, sound not coming.
Sound not coming again. Yeah, now?
Audible, sir.
Yeah. So this is V1, this is let's say Vc, this is my L, this is my current IL. So what equation can we write from here? And yeah, so L, so there is no circuit as there is no ideal circuit, right? So for that, what uh, is considered is the L is also accompanied by a RT. There will also be an, let's name it R. So let's write the expression V1 minus Vc is equals to ILR plus LdIL by dt. This can be written. Yeah. Hello. This can be written, right? This expression. Hello, hello, hello. Am I audible? Hello.
Sir, voice is not coming, sir. Sir. Yes, sir. Audible.
Okay. So now, so this is the KVL expression that we can write in case of inverter. Just say yes or no.
Yes, yes, sir.
Okay. Now what we are going to do is we will be applying Park transformation. Now what is Park transformation? It's not mentioned in the lecture. So it's basically in machines, what we do in mostly in synchronous machines, we represent the current in terms of its in phase component or direct component and a quadrature component, right? So what here we will be doing is, V1 is a sinusoid, right? V1 average for 50 hertz, if we consider, it can be written as Vm1 sine of 2 pi ft. Yes or no? Yeah. Hello.
So yes, maybe sir, అంటే earlier you are writing V1 at 50 hertz frequency is equal to M modulation index into M into
Yeah.
sin
So
omega.
yeah, m. So it's basically what, m by 2 VDC Vm1, right? So here the m comes.
Okay, okay.
So uh, this expression can be obtained if you do the steady state analysis for inverter. I think it is in the fourth lecture, this how to derive in case of inverter. So just consider it is something like this: m by 2 VDC sine 2 pi ft, where f is 50 hertz. Now can we ensure that IL is also in phase with V1? We cannot, right? Because we do not know the load. So we cannot ensure that IL will be in phase with. So let us consider in terms of phasor. If this is V1 and let's say this is my IL, what I will say is this is my ID and this is my IQ. Clear? So in phase component with the inverter voltage, we will consider it to be the direct component, and out of phase component will be considered as quadrature component. Clear or not? Any doubt? Similarly, we can go for VC. Let's say VC is something like this. This is VC. So the direct component is VCD and the quadrature component will be VCQ. Clear?
Sir.
Okay. So hence what we can write. So let me write it clearly so that you can understand it properly. Once we have established this,
Sir, audio is not. Sir, no sound, sir, no sound.
Is it audible now? Hello.
Sir, now it's audible, sir. Yes, sir. No, sir. Sir, why we are putting a capacitor instead of putting any source side of directly connected to the load, or why we are putting the capacitor instead of going for the this direct connecting to the converter from the conversion end or load end. Okay. After getting converted to the some PV directly, PV to DC converter, then again inverter kind of thing. Ah, okay, okay, that is. Sir, again power no sound, sir. No sound.